Hello, my name is Stacey Martin. I work with the science team here at Ed Rollo. Part of my role in developing quality resources is looking at current research about how students learn and how we can help make learning stick. So today, I want to share some of what I've discovered with you, particularly around the use of scientific models. Almost all of the examples I'm using today come straight from our 7 to 10 science resource. Models are a way for us to help represent, describe, and explain the material world. Much of what we explore in science is invisible to the naked eye, making models an essential tool in the classroom. You're bound to use models in most of your classes, but being aware of how or when to use models, we can slow down thinking and encourage deeper, more imaginative engagement with scientific ideas and reason through complex concepts. Some examples of models are physical models. These are tangible representations such as a globe of the Earth, Mollymods, creating a 3D cell, a DNA double helix made from lollies. We have computer models. These are simulations that use algorithms such as climate models, weather patterns, and population data. Mathematical models, these use equations to represent relationships such as F equals M times A. And we have conceptual models, which are abstract representations, often using diagrams such as the water cycle or the atom. And another type of model you'll be familiar with, the supermodel. A model is often best introduced after a scientific explanation. If used too early, students may focus only on its literal parts and miss its explanatory power. A single model can serve multiple purposes, such as explaining a concept, testing predictions, or visualizing processes. Often more than one model is needed to fully understand complex scientific ideas, as different models highlight different aspects of a concept. Understanding where your students are in their learning journey is crucial to deciding when and how to introduce models effectively. You need to gauge what your students need and how best to guide them to that understanding. One of the biggest challenges in teaching science is helping students understand concepts at different scales. As science teachers, we're used to moving seamlessly from the molecular level and then to the macroscopic world. But for students, this isn't always easy. When we show a simple diagram of an atom or a chemical reaction, we see the science behind it. But students often just see shapes and letters. For example, when I first taught students about cells, they could easily label cell diagrams. But when I asked them where they might find cells in the real world, they weren't all sure. They couldn't actually connect the labeled diagram to the bigger picture, the organism. This is where models can come in. They can allow us to zoom in and out and bridge that gap between the visible and invisible. They help students visualize complex concepts and see how small-scale components fit into larger systems. What's important is to guide students through this process. If we can help them zoom in on the details and see how these details fit into a bigger picture, using models intentionally, we can help students grasp the connections between the scales and deepen their understanding of scientific ideas. Making science relatable to students is one of the best ways to get them engaged, and that's where analogue models come in. These are models that can take an abstract concept and relate it to something concrete and familiar. They help students build connections between the unknown and the known and make these ideas much easier to understand. For example, an electric circuit can be compared to water flowing through pipes. The current is like the water, the voltage is like the pressure, and the resistance is like a narrowing pipe. Students can grasp this because they already understand how water moves through a pipe. It's something they've seen and experienced before. This allows students to anchor new information to something they're already familiar with. Instead of being overwhelmed by the complexity of a new concept, it makes the content not only more accessible, but also more memorable. This example looks specifically at the particle model. Students are usually familiar with this by the end of year 7 or 8, but sometimes they don't think about it again. However, it's taught early as it underpins so many scientific concepts, such as the different states of matter, as well as temperature, diffusion, conduction, kinetic energy, expansion, and contraction. So on the left, we see 2 different substances, oxygen, which is a gas, and gold, which is a solid. By zooming in and showing the particles, students can see how the particles in a gas are more spread out, while in a solid, the particles are tightly packed. We're also highlighting here that these are both pure substances as they contain only one type of particle in each. We'll touch on the limitations of these models later. As students start to learn about temperature, they can connect the particle model again. By understanding how particle movement changes with temperature, students can see why gases expand and solids stay rigid at different temperatures. This visual representation helps clarify why gases and solids behave differently and reinforces the abstract concept of temperature in a more tangible way. Here you can see all the stages of the water cycle represented. Each of these processes is interconnected, and this model makes it easier for students to grasp how water transitions between different states and locations. By showing the connections, students can see how the water cycle sustains ecosystems, impacts weather patterns, and helps regulate Earth's climate. It also allows them to ask critical questions about where water goes, how it changes form, and why it's crucial to life on Earth. You could even bring back the particle model to reinforce concepts and help students connect ideas here. Food webs are another example showing how energy and matter transfers through a system. Interpreting these models is a skill, but by teaching students how to unpack these models, they'll be better able to understand scientific phenomena and predict, test, and analyse ideas. These models can help students understand systems more deeply and think critically about scientific concepts. What's great about comparing representations is that it helps students understand not just what happens during a chemical reaction, for example, but how the atoms are rearranged. The symbolic equation shows the reactants and products, while the molecular model makes it easier to see the physical structure and movement of atoms during the reaction. By providing both, students get a complete picture. They can understand the equation abstractly and then visualise how the molecules actually look and change. Another example of this includes the arrows representing forces at play. When first learning about how to model forces, it's much clearer to students if we can connect the model to the real world so that they can see that these forces are not just theoretical. This approach helps students grasp challenging ideas by linking them to their experiences while lowering cognitive load. It helps make learning more intuitive and shows how the concepts apply to the world around them. When we use models, we have to remember that while they have many uses, they also have limitations. Even supermodels like Zoolander, who can't turn left, and Kendall Jenner struggles to cut cucumbers. It is important to be aware how these limitations can affect understanding. The particle model of matter, where atoms are shown as solid spheres that vibrate in place in solids, move freely in liquids, and fly around in gases. Again, this helps us understand the concept of states of matter, but it misses important details like the fact that atoms themselves are mostly empty space and their behaviour is influenced by quantum mechanics. The Bohr model of the atom shows electrons orbiting the nucleus like planets around the sun, great for teaching basic atomic structure, but it oversimplifies how electrons behave. In reality, electrons don't follow fixed paths around the nucleus like planets do. Instead, they exist in clouds, which is far more complex and less predictable than what this model shows. Similarly, when we look at models of the solar system, we often show the sun and planets at a convenient scale for us to see them all at once. In reality, the distances between the planets are far greater than what is depicted, and the size of the planets relative to the sun is also vastly different. Models of cells are great for showing organelles, but they don't represent the dynamic, constantly changing nature of what's happening inside the cell. Cells are much more crowded and organelles aren't as clearly separated as they appear in static models. You might be familiar with Mrs. Gren, a conceptual model that is commonly used in biology to help students determine whether something is living or non-living by checking if it meets all these essential characteristics. However, while Mrs. Gren provides a useful framework for understanding life, it also has limitations. Real-life organisms may exhibit these characteristics in complex ways or may not even fit neatly into every category. For example, hybrid species like the mule are often infertile and cannot reproduce, but they're very much living. So while models are fantastic tools for visualising and explaining scientific ideas, it's important to teach students to recognise their limitations. Models simplify reality, and by acknowledging what they leave out, students can develop a deeper, more nuanced understanding of science. As teachers, we want to engage and motivate students and be creative in our teaching. Helping model abstract ideas that can't normally be seen helps students create meaning. Classroom activities can help teachers see what students are thinking and provide an opportunity for students to discuss and reason with scientific ideas. So a few ways to incorporate this include having your students build models of model processes using claymation or other crafts materials, looking at historical models. How has the atom changed over time, for example? You could play Pictionary, have students pick a key term out of a hat and then draw that key term on the board. Or Supermodel, have students be the model, perform and act out a process or model a concept. Incorporate discussion about the advantages and disadvantages of models that you can use, and this can also be done with theoretical models such as evolution. This helps to identify misconceptions, it'll make students' learning visible to you, it will assess their understanding, and then allow you to provide instant feedback. Some questions to think about include, can students explain the model in their own words? Can students recognise the limitations of a model? Can students propose improvements or modifications to a model? Can students design and assess their own models based on a concept? Thank you for watching. I hope you found this useful. You've been a model audience. If you have any questions, queries, qualms, concerns, comments or quandaries, please let us know.